As mentioned before, my PhD was done at Riga Technical University under the supervision of Professor Dagnia Locha and Professor Yanis Lochis. So, when we first started to discuss the topic of my PhD, we went to the basics and observed the structure of the bone. As we all know, the inorganic part, which is almost 70%, is represented by non-stoichiometric hydroxyapatite. And the entire process of bone formation starts from ACP Posner clusters, which undergo calcium uptake, convert to octacalcium phosphate, which undergoes additional ion exchange, and finally transforms to biological apatite. Considering that this bone formation process is very important, we have decided to put focus of our research on one of the bone precursors, octacalcium phosphate. However, during the literature search, we noticed that the research on OCP is not that popular, even though the advantages of OCP are very connected to its structure. The structure of OCP is very specific. It's made of interlaying parts of apatite and the water layer. And the presence of the water layer gives an additional benefit, which is the possibility to incorporate different drugs and ions up to a certain extent. However, both of these benefits can also bring out the challenges of OCP. The similarity to hydroxyapatite makes the phase quantification very hard, and the presence of the water layer makes it difficult to process and utilize OCP. There are two ways to synthesize it, hydrolysis and precipitation, and for both of these, it's crucial to consider pH, temperature, stirring, and dose rate. Not optimizing one of these parameters in a perfect manner can lead to a completely different phase being formed or a mixture of various calcium phosphates. Having all the benefits and possible pitfalls in mind, we have divided our research goals into two parts: synthesis of OCP and utilization. After spending many moons in the lab, changing parameters, precursors, and failing many times, we have finally optimized our chosen synthesis pathway and decided to continue with the low-temperature alpha TCP synthesized from ACP for 24 hours. XRD confirmed the presence of OCP, and as we can see, the very specific XRD maxima of OCP includes the intensive peak at low 4.72 theta degrees and a doublet at 9.4 and 9.7. As we said, OCP is quite similar to hydroxyapatite, which is why it's important to look at its molecular structure. We performed FTIR and Raman and confirmed the presence of the hydrogen phosphate ion, which is very specific to OCP. SEM displayed the plate-like morphology of OCP particles with a size of 1 to 2 microns, and with DEM, we noticed that the particles have a very big tendency to agglomerate, which the size of an individual crystal goes almost to 200 or less nanometers. Even though we got a very nice OCP, the problem was that we had only 100 milligrams per batch of product. And if we were to utilize it in any way, the yield was just not enough. In order to increase the yield of OCP to 1 gram and 10 grams, we needed to optimize the methodology again, and we decided to keep the solid to liquid phase ratio the same, and to see when we will obtain OCP. To understand the formation mechanism, we sampled the synthesis at different time points and tested it with different techniques, and due to the time, I will present the results only for the largest scale-up model, which was 10 grams. In the first hour of the synthesis, we still had only alpha TCP, but already at 24 hours, slight presence of OCP can be noticed with a substantial maxima at around 12 theta degrees, which belonged to bruchite. However, over the time, both the OCP maxima and bruchite maxima intensified, with alpha TCP no longer being present. From 96th hour up to the end of synthesis, bruchite slowly disappeared, leaving the OCP phase alone. Together with precise pH measurements, we managed to pinpoint the steps of OCP phase formation and obtain a very high yield of the product. All of these already obtained XRD and FTIR data from the 100-fold synthesis were additionally analyzed, and with the help of our colleagues in Italy, we managed to develop a pilot algorithm that will recognize at which point the synthesis stage is, and it gave a very high potential for use in industry. The second part of the research was the utilization of OCP. And to utilize it, we have chosen two roads: creation of drug delivery system and development of coatings for metallic implants. For the drug delivery system, doxorubicin hydrochloride was a chosen drug, as it has been used for a very long time, but it showed a very high systemic toxicity. And for the coatings, we have used alginate in order to test will it improve the corrosion resistance. In both of these pathways, the main focus was to preserve OCP phase. Considering that the OCP phase is very tricky, as we already saw, first we tested how much doxorubicin can be incorporated. We used concentrations from 1 to 20 weight% of the theoretical loading and added it in situ during the synthesis. With XRD, we saw that up to 10 weight% OCP phase was still present, but everything above completely inhibited the formation of OCP. When we looked closer, we saw that the main maxima at 4.7 has shifted toward lower values, with higher amounts of incorporated doxorubicin. This was a strong indication that the drug was not only absorbed on the surface, but also incorporated in OCP. With SEM, we also saw the plate-like morphology of OCP in the concentrations up to 10 weight%, whereas 20 weight% had a thread-like appearance, same as the used precursor, which was alpha-TCP. In the second step, we tested the drug content and release of our system. The maximum detected drug was approximately 2 weight% from the 10 weight% doxorubicin octocalcium phosphate system, and all the tested samples had a very high initial burst release within the first 24 hours. Nevertheless, all of them had a sustained release up to 6 weeks. The final step was to test our doxorubicin OCP in vitro with both the cancer cell lines and healthy cell lines, and we saw that both cell lines in the first day had a very low cell viability, but at the 7th day, healthy cell lines started to proliferate, whereas the cancer cell lines did not, which was a very good indication for future use. Additionally, we expanded the osteosarcoma choice of cells, and with cleaved PARP, we saw that the apoptosis was the main pathway of cell death. For the second utilization of OCP, we have developed composite coatings with alginate in order to increase the corrosion resistance. We have tested it in 3 different media that simulated normal body conditions, inflammatory and severe inflammatory. And in all the testing conditions, OCP mostly remained after the immersion, and the electrochemical tests proved that for 2 different titanium grades, incorporating OCP in alginate had significantly higher resistance than bare titanium or only alginate-covered titanium. With this, we finalized both parts of our research, and we saw that the scale-up yielded 10 grams of OCP, alpha-TCP transformed to OCP through brushite. When the drug was incorporated, over 10 weight% inhibited OCP phase formation. Doxorubicin OCP systems had a continuous release over 42 days, whereas healthy and cancer cell lines had a time and concentration-dependent decrease. When we incorporated OCP in the alginate matrix, it increased the corrosion resistance. Throughout all this work, I have to thank all of our collaborators and both of my colleagues and partners together with the Marie Curie project, Premurosa, Rises 2 project, and Baltic Biomaterials Center of Excellence for making it all happen. Thank you again for listening, and I hope you enjoyed.